Welcome everybody to a new Innovators Update. My name is Richard Holskes. I am the co-founder of wearable.com. We are back as always with Rachel Gordon, the Communications and Media Officer at MIT. And she has invited a computer scientist this time from MIT to speak with us. Rachel?
Hi, Rich. Thanks for having me. Today, we're going to be speaking with Joseph DelPreto, who is a PhD candidate at MIT CSAIL. He's working on making human-robot interfaces more accessible and effective by using wearable sensors and biosignals. Joseph, welcome.
Hi, Rachel and Rich. It's great to be here.
So, Joseph, Albert Einstein famously postulated that the only real valuable thing is intuition, arguably one of the most important keys to understanding intention and communication. But intuitiveness is hard to teach, especially to a machine. Your method takes us closer to seamless human-robot collaboration. You're leveraging muscle signals from wearable sensors to pilot a robot's movement. Where did this idea to incorporate muscle movements to control a robot come from?
Well, ultimately, we want to try to make working with a robot as easy as working with another person. And when you work with a teammate, you typically have an intuition of what they're trying to do and how they're trying to do it. Like if you think of trying to lift a couch with a friend, right, you'll probably have a sense of which direction they're trying to move, how high they're trying to lift, whether they're getting tired, even if they don't explicitly tell you any of that. And these types of cues can be hard for a robot to pick up on typically. But we were excited to try to use muscle signals to help with that and detect more of these physical states. And so hopefully that can help us pick up on more of these nonverbal commands and make it a bit more fluid to work with the robot. And muscle sensors can also be very small and wearable, which helps us reduce the amount of hardware that a person needs to set up so they can start working with a robot more quickly.
All right, so Joseph, did you have to create a new technology for the system, or did you modify existing electromyography or EMG technology?
Yeah, so for the most part, all the hardware that we use is actually off the shelf, and we focus more on the algorithms for processing that sensor data and using it to control a robot in a useful way. So, for example, we use a commercially available armband that you can slip onto the forearm, and it has some EMG sensors around it to detect muscle activity. And it also has an IMU, or an inertial measurement unit, to detect motion data. And just as a quick background, I guess, on EMG in general, it's basically a small antenna that you can just stick onto your skin, and then it will pick up on the electrical impulses that go through your muscles when you tense them. So it's actually a relatively simple sensor, at least in principle, but it lets us detect some really neat physical states like force or stiffness or even fatigue. So we can put these on the forearm to detect hand motions and hand activity without actually putting sensors on the hand itself, which can help us be a bit less obtrusive depending on the task. And we can also put them on, say, the biceps and triceps to detect more upper arm activity for bigger motions.
So, Joseph, now that we know about the hardware, I'm curious about the decision-making process. Is the robot continuously learning and able to inform future decisions based off of previous movements?
Yeah, so far, most of the learning that the system does is actually based around adapting to differences in muscle signals, like between people or over time. So, for example, if you and I both put on the muscle sensors and started working with the robot and lifting things, we will probably detect different levels of muscle activity between us. And as we keep working and we get a bit tired, the muscle signals will change even more. So, we designed the system to automatically accommodate those differences and to adapt as you continue working. So, as you continue making gestures and lifting an object, it will automatically find good thresholds and change its detection pipelines to continue having the robot respond appropriately. And for some of these gestures to do this, we use a neural network. And for others, we use a more clustering based approach where it finds a threshold as you go and learns to distinguish between muscle sensors without having training data ahead of time. So hopefully, approaches like this can go a long way towards making it easier to start working with the robot, since we'd like the person to just be able to put on a sensor and immediately start interacting with the robot instead of having to provide a lot of calibration data or training data.
That's really interesting, Joseph. And can you tell a little bit more about what types of tasks RoboRaise or the Conduct-a-Bot can currently accomplish? Like maybe you can also talk about some of the future applications that it might have.
Sure. So far, the two main tasks that we've looked at are sort of direct physical collaboration and also remotely controlling a robot. So for the direct physical collaboration, we were looking at team lifting. So basically, the robot would hold one end of the object, I could hold the other end of an object, and we try to lift it up and down together. So for that, the robot can just look at the biceps and triceps muscle activity to get a sense of when I'm lifting the object up and down. And then it will try to mirror those motions to keep the object level. But then the person could also just tense or relax their arm a bit or make gestures to fine tune the robot's behavior. So it's sort of like, again, if you were lifting a piece of furniture with a friend, you'll probably try to keep it relatively level, but then you can also get like these nonverbal cues of when to lift your end higher or lower. So hopefully this could be helpful for like assembly or construction tasks in industrial settings or even in home settings too. Then, in addition to this direct collaboration, we were also looking at remotely controlling a robot. So, for example, we've had people pilot a drone around the test area just using a gesture vocabulary that we detect using this wearable muscle and motion sensor. So, you could imagine using this for like a survey task where you're remotely piloting a robot to take sensor readings, or when you're directly controlling a robot in a dangerous place or a dangerous task where a person shouldn't necessarily be. And in terms of future applications, we're really interested in having the robot learn more about the task in general as it's working with you. So far we've focused on these interfaces for making it more natural to control the robot, whether it's working with you or working somewhere else. But it'd be great if the robot could then learn more about what you want it to do and become a bit more autonomous to provide more proactive assistance.
So, beyond the applications that you mentioned, self powered personalized medication has seen really great improvements with technology. So, are there any potential medical applications here? For example, for someone who's had partial nerve damage and has lost function in that area, could this technology be adopted to assist with functional movement? Or could it even be incorporated into an in home living assistance setting for nursing homes or help with people who have specific needs?
Yeah, so far the systems that we're working on are still in the research phase and we've tested them out with healthy subjects in a lab setting. But I definitely agree that applying these technologies to more assistive devices would be a really impactful way to use these systems. And in fact, a lot of people do already look at using muscle signals for rehabilitation, for prosthetics, and for general assistive devices that can help improve quality of life. So I'd be really excited to try to use some of the algorithms that we've developed and these ideas for these interfaces to help develop some of these a bit further in the future.
All right. Hey, and most importantly, what happens when my arm gets tired?
Yeah. So that is a really important consideration, actually. And it's something that we always have to consider when we're making like these gesture interfaces or physical interfaces in general, right? Like using gestures to control a robot can get tiring. So in terms of the classification pipeline for us, it should automatically adapt to these different muscle signal levels as you continue making gestures. So the robot should hopefully still respond appropriately. But in terms of the larger like user experience and how to best accommodate that, that's still an open question that we're still looking at. But one of the advantages of using muscle signals is that we can detect this fatigue, hopefully. So it'd be great if the robot could maybe adapt how it's assisting you, take on more of the load in response to this.
All right. Well, exciting things to come, I guess, in the future as well. Um, I guess that's it for this time, folks. Thank you so much both for your time, Rachel, Joseph. I really appreciate it. I think our audience will appreciate it a lot as well. I also look forward, Joseph, to seeing your future work, and hopefully Rachel will share more of that on our platform also. For our viewers and listeners, they can find the interview on wevolvo.com. We'll also publish it on as a podcast on Apple, Spotify, and any other medium that you follow. You just have to look for the Innovators Update. That's it, folks. Thanks again, and we'll talk later.
Thanks so much, Joseph. It was great speaking with you.
Thank you. It's been a pleasure.
Bye-bye.